I'm Tim Ventura, and we're joined today by Max Fomitchev-Zamilov, the founder of Maximus Energy Corporation, which refurbishes and manufactures nuclear instruments, including neutron and gamma detectors. Prior to founding Maximus Energy, Max was a professor of software engineering and computer science at Penn State, with a PhD in ultrasonics. Currently, Max is working on microscopic thermonuclear fusion, what appears to be a new form of bubble fusion, and his latest results were published in Nature Scientific Reports in May of 2024. Max, welcome, sir. Today we are talking about something that is similar to bubble fusion. You're going to walk us through the details of it. We have a PowerPoint, which is a rare thing on my channel, but let's get into this.
All right. Well, Tim, thank you very much for having me. My name is Max Fomitchev-Zamilov. I'm the founder of Maximus Energy Corporation. And for the past 3 years, I've been working on what I call microscopic thermonuclear fusion. And the way I observed it is by way of monitoring neutrons. But first things first, you all probably heard about bubble fusion, which made a splash maybe 15 years ago or so when Teleyarkhan reported his groundbreaking observation of neutron emission when cavitation bubbles in deuterated acetone were expanding and collapsing. And this is not really anything strange in the sense that the physics is well understood. And the idea is very similar to internal confinement thermonuclear fusion. So basically when the bubble expands and collapses, the temperature inside it gets hot enough for deuterium-deuterium fusion to take place. And in fact, this very similar idea is massively pursued by National Ignition Facility, which is a multi-billion-dollar installation here in the US, where about 200 lasers focus their light on a fusion pellet. And that fusion pellet is a bubble of solid deuterium and tritium water. And the laser beams heat up that bubble and force it to compress. And lately, they reported that for the first time ever, that bubble produced more nuclear energy than went into its collapse, but it doesn't mean it achieved any sort of net energy production. But bubble fusion idea is very similar. But for it to work, we need to take a bubble and expand it about 1,000 times. So math and basic fluid dynamics tell us that the bubble needs to be expanded about 1,000 times of its initial diameter. So if the bubble was a micron initially, it needs to be expanded to 1,000 microns or 1 millimeter. And when it collapses, it needs to collapse spherically. And if it does not collapse spherically, we cannot expect fusion to take place, and this is known as instability. So the National Ignition Facility project is plagued by instabilities, and unfortunately, bubble fusion is also. And on this picture, you see that when the bubble is collapsing, it's typically forming a jet that penetrates the bubble and basically destroys the bubble. So this is a very well-known instability. So when I started this project, I knew that these instabilities would be a problem, but I decided to try anyhow. And this is the setup I've built. And this is the setup you see behind me in the video frame. It looks a little messy because there are many parts, so it's best if I used this picture to explain what it is. So at the heart of this setup is the bubble fusion reactor, which is a stainless section of 6 inches in diameter that's filled with oil, with mineral oil. Yeah, and you can see it there. Then we have a piezoelectric driver mounted to the bottom plate of that reactor, which you can't really see because it's under the table, but that is the system that generates sound, that pushes acoustic waves into the oil. Also, what you see here is a pump, a Venturi nozzle, another cavitation reactor, and a couple of valves. This is our circulation loop. So sometimes I use this loop to run oil through the Venturi to saturate it with bubbles. And behind you see the laser diffraction system that I use for bubble size measurement. So when I generate the bubbles using Venturi, and deuterium lecture bottle is connected to here, I want to measure what sort of bubbles I get, and that's what this laser is for in the back. And this is a vacuum system to keep pressure inside the reactor. And this is the microphone or another acoustic transducer that I use to monitor the sound. So this is, the gist of it. And here is a close-up look of the reactor. And here you see that the oil looks grayish because it is saturated with deuterium nanobubbles. And that's, where my starting point was. I wanted to saturate my oil with deuterium nanobubbles and discover, the conditions that would result in fusion. And out here, I actually experimented with heavy water droplets. So this is technically an emulsion, so it's different in color. And you see also that the glass cracked, because one of the things I discovered is when I work with emulsions, the acoustic waves are much, much stronger than one would expect. And I'll talk about that in just a second. But my reactor, unlike most fusion reactors, is probably closer to a solid state reactor because I don't work with plasmas. And as you know, plasmas are generally vacuum. So I use liquid targets, and my working fluid is mineral oil. And this is the schematic diagram of the reactor, which I already explained. So this is the piezo driver, which is powered by Branson sonifier, which is below the table, which you cannot see. And this is my acoustic transducer that I use to read the strength of the sound. And how do I know that my reactor does anything? Well, I have this helium-3 neutron detectors mounted to the side of the reactor. And those are connected to the hardware that I manufacture at Maximus Energy Corporation, the automated nuclear lab. So by looking at the neutron detector signal, I can tell whether the reactor is functioning or not. So these are the kind of detectors I use. These are helium-3 proportional neutron counters. This particular one is a bank of 6 made by L&D, and I assembled them in a bank. And this is a thermal neutron spectrum. So when the neutron detector tube detects a neutron, it generates a pulse that looks like this, and then the software counts those pulses and builds a pulse height spectrum. And at the end of the day, the spectrum needs to look like a thermal neutron spectrum, and this is how I know that I'm counting neutrons and not noise. So this is, a rather technical topic, but an essential one, when you're dealing with nuclear science. And this is the automated nuclear lab hardware that I specifically designed for the purpose of this experiment. So this is a multi-channel analyzer and pulse processor that I also manufacture, and a bunch of other researchers, including MIT, are using it now for their experiments. And it runs under the control of pulse counter software that I also developed. So a side note here, when I started my nuclear research, 5 years ago or so, I was appalled to see that, there was no accessible hardware available for neutron or gamma detection that could meet scientific needs in the budget. And that was the motivation for me to develop my own hardware and software, because at the end of the day, you don't only need to capture, let's say, your total counts. You need to capture the entire raw data set that you can analyze and reanalyze later on, because scientists like to scrutinize things. So if you publish a claim and say something happened and you don't back it up with sufficient evidence, nobody's going to believe it. So that's why I had to develop software that captured the entire detector signal and was transparent as far as the pulse shaping and pulse counting goes, and spectrum reconstruction. So all of that was necessary in order to prove to my colleagues and to myself that what I'm measuring are indeed neutrons and not noise like from ground loop or something else. And here's a good example of why this software is necessary, because we often forget that when we deal with nuclear science, we're dealing with random processes. Meaning, if you take a single measurement, it's utterly meaningless. So let's say you have a neutron detector and you take a measurement, and it tells you had 17 counts per minute, like this bar shows here. Well, it means nothing, because all nuclear processes are random in nature, which means if you take one measurement, it could be 17. You take the next measurement, could be 100. You take a third measurement, could be 0. You take fourth, could be 1,000,000. It's a random process. So the numbers you get random. And the only way to make sense of it is if you capture enough of this, and when you have enough of this, they will start building a distribution. So it will be either normal distribution or Poisson distribution in this case. And what you see here is two Poisson distributions that correspond to two sets of measurements. One is the experimental measurement, the blue chart, and the other is background or control, the red chart. And as you can see, individual measurements overlap. And just by eyeballing it, it's hard to tell whether these two distributions are the same. But because we captured enough data sets, and then we can do statistical analysis, and we can do a student's t-test and evaluate a p-value, and it will tell you what is the probability that two distributions are in fact the same. And I know it's a very technical topic for a non-technical person, but it's an essential step that a lot of amateur physicists or amateur experimentalists overlook when they work with nuclear science. They take a single measurement and they think it's meaningful. But the truth is you need to take a bunch of measurements and you need to do statistical analysis to show that your result exceeds background. And this is what I do with this pulse counter software that I developed. And this is a typical experimental setup. This is how it looks at the end of the day. Red bars here correspond to background measurements, and blue bars correspond to experimental counts. So when I count background neutrons, and there are background neutrons because there are cosmic rays and there is radioactivity, so we always have background neutrons. I get between 0 and maybe 10 or 11 counts per minute. But then when I turn on the reactor, and the counts correspond to blue bars, and a little bit higher. But once again, it's hard to tell unless you do the statistics. And once you do the statistics, this is a summary here. It says that the background counts are, experimental counts are about 40% higher than the background counts. So this blue bar is about 40% higher on average than the red bars. And this black chart is the p-value trend, which, the more experiments you run, it needs to approach 0. And that's, in fact, what we see here. The more experiments we run, it basically became, less than, 1/1000th. So this is, statistical, burden of proof that is expected of a scientific quality work. And this is the acoustic pulses that I get inside my reactor. So the driver, the acoustic driver that you saw on the diagram, generates 20 kilohertz sine wave. So this is this smooth sine wave that excites the oil with bubbles inside the reactor. And these spikes is something interesting that I started observing when I introduced heavy water droplets inside my reactor. So these spikes are on the order of tens of thousands psi. I think they happen because heavy water droplets vaporize, and those bubbles expand and collapse in unison, creating outgoing shock waves that constructively interfere. And these shock waves form these massive acoustic pulses. And this is something new, worthy of publication on its own right. And those are the massive pulses that broke the glass of the reactor on more than one occasion. So basically, these droplets that I introduced create sound that's super, super strong, 1,000 times stronger than the sound of the acoustic driver alone. And I think this is the essential component of my reactor operation. So here is the best result that I've gotten. Let me explain what you're looking at here. I think the main chart is this: it's the count rate history. So if you recall, let's say the previous slide, the background counts were on the order of maybe 12 counts per minute, and these are counts per minute. And the background is so small you cannot even see here, because this is 500 counts per minute and this is like 1700 counts per minute. So for many days I was experimenting with my reactor and nothing was happening. My counts were on the order of background. But one day, all of a sudden, I started getting these massive spikes of neutrons, like 100 times in excess of background, to where you don't even need to do statistical analysis. It's so strong. So of course I was very curious to see what my neutron detector signal looked like. So I captured the raw data set, and each vertical line here is an individual neutron pulse. You see there are so many of them, they like almost overlap. So if I expand this, I see that my signal contains a little bit of noise. So there's little clumps. Oops, sorry, I skipped. Okay, so this little clumps of noise correspond to the acoustic coupling between the, capacitive coupling between the piezoelectric driver that supplied the sound to the reactor and the neutron detector bank. But luckily these noise clusters are small. They're much smaller than the neutron signals, and these neutron signals are these vertical lines. But the important thing of this is that you see that these neutrons, which are vertical lines, appear predominantly when the sound is turned on. So every time the sound is turned on, we see this in a little clump of noise. And almost every time when the sound is on, we see, these acoustic pulses, and then very few of them in between, like I only see one of them in between. So this tells me that my neutrons are synchronous with sound, and that's what you would expect from, from bubble fusion when your fusion is driven by acoustic cavitation. So I was very happy to see this result, and I proceeded to conduct another test. So on this result, you see that for about 24 hours, I captured background. And this time, background is counted as counts per second as opposed to counts per minute. So basically, take your counts per minute, divide by 60, you get your counts per second. So I wasn't getting even, 1 neutron per minute, or, like 1 fraction of a neutron per second. And then when I turned the reactor on, you see my neutron counts increase. I turned the reactor off, they return to background. I turned the reactor on, my neutron counts increase. So one thing I noticed, the longer I operated my reactor, the higher the neutron counts were. And this is kind of consistent with the idea of thermonuclear fusion, because as soon as deuterium starts fusing, you start getting tritium, and tritium is more likely to fuse. So yes, you'd expect your neutron counts to go up as your reactor keeps on running because you're breeding tritium. And on some of the acoustic events, I had multiple neutrons that originated. And in this case, we have 1, 2, 3, 4 so closely spaced together they cannot be resolved. But that's also a pretty good indicator telling me that not just one, but several neutrons are produced because there are multiple bubbles in the reactor. And the last thing I had to do in order to get publishable quality results and to convince both myself and my colleagues that indeed I'm counting neutrons, I operated my reactor for several hours. And when the reactor runs for several hours, you should get enough neutrons to where you start seeing this nice thermal neutron spectrum. And that's exactly what I did. I captured the thermal neutron spectrum over 1 hour of reactor operational time. And at that point, I knew that I have enough information to publish my results, which I did in May issue of Nature Scientific Reports. My paper came out entitled Observation of Neutron Emission During Acoustic Cavitation of Mineral Oil with Titanium Deuteride. But more on that in just a second. Here, I would like to report some inexplicable result that I could never make sense of. And once again, let's look at this chart at the bottom. So blue is the background, red is the experiment. So I start the reactor, counts going up. I turn the reactor off, counts go down. I start the reactor, counts go up. I turn the reactor off, and much to my surprise, counts do not return to baseline instantaneously. And that's what you would expect if this was, truly a bubble fusion process. Because once you turn off the sound, there is nothing to expand or collapse the bubble. So how come neutron counts don't return to baseline instantaneously? And you see, I've repeated this, several times, and every time, I saw the same behavior. So this told me that, the process that I stumbled upon isn't, bubble fusion, it's something else. And truth be told, I don't know what it is to this moment, and I'm continuing to research it. But this, result is inexplicable from the standpoint of standard bubble fusion, because neutron counts must return to 0 as soon as you turn the reactor, turn the sound off. But so, what do I know and what I don't know? So unfortunately, I cannot boast that, I've mastered the complete understanding of this process. I think I just, scratched the surface, and my understanding is rather limited at this stage, and I continue working on it. But, one thing that often happens when you experiment is, some luck, some lucky chance, helps you. And that lucky chance helped me because I mixed perfect working fluid by accident. In fact, I was keeping a waste bucket when I was running my experiments, and I was dumping oil from the reactor into the waste bucket. And once, I didn't want to use virgin oil because it was running low. So I took oil from the bucket, and that's when I've gotten my best result. Well, the oil in the bucket was heavily oxidized from use, so it was yellow in color, and it probably contained some copper, so because I used copper gasket, so it was yellow and green in color, to be precise. And, you can see borax boxes in the back, so it might have been some borax have gotten into it. So I know for a fact that my oil contained DTO droplets because I introduced heavy water, and it did contain some titanium deuteride particles because in some experiments I used titanium deuteride powder. And, some of other chemicals that I used on and off, but I think, those are, the most significant ones that I mentioned. Also worth noting, when I was pumping oil through the circulation loop, oil was receiving significant static charge when I was filtering it. So that may be important because once your particles are statically charged, they are far less to coalesce, and your emulsion or suspension is more stable. And there was a wide range of pressures and and oil concentrations when the reactor operated. So it was from low-grade vacuum down to atmospheric pressure. But most of my experiments were performed at about between 4 and 20 torr of partial vacuum. And the concentration of emulsion also varied from very thin to very thick, basically from opaque to clear. So the more opaque was the emulsion, the more neutrons I was getting. So clearly there was a correlation with how many bubbles or droplets I had. And most importantly, my results were repeatable for many months. For about 6 months, while that emulsion lasted, I was able to operate with it, and I was able to sustain the reactor operation for hours. So I was in a pretty stable emulsion. And unfortunately, in about 6 months, it ran out. And now I'm trying to recreate that magic recipe that I had, but so far I have not succeeded. And that's where chance on one hand helps you, on the other hand complicates your work. But that's how the discoveries are. You stumble upon something and happen rather quickly for me, but it takes it's taken me almost 3 years now to try to figure out how to mix that emulsion. So I'm still working on it, trying to do it one more time. So what I don't know, well, I cannot claim that my neutrons were from fusion, because scientific level of precision requires to capture either a neutron spectrum, meaning I need to know what energy of the neutrons are, and my neutrons are thermalized, which means they pass through moderator and lost that energy. So I cannot tell by looking at the spectrum whether those are fusion neutrons or not. And there are other nuclear processes like spallation that could result in neutrons. So I cannot make the claim that I've observed fusion. That's why I say I observed neutrons. But there are only two processes that we know of. One is spallation, and the other is fusion. And I think indirect evidence for fusion is that the neutron count goes up as the reactor keeps running, because that's what you would expect from tritium being bred inside the reactor. Well, I don't know, as I said, the exact composition of working fluid. I know some of the components that are in it, but I don't know the concentrations or the particle size distributions, and that's what I'm trying to recreate now as I continue to work on this project. But the biggest mystery, of course, to me is why the neutron signal didn't return to baseline instantly when I turned off the acoustic excitation. And that's why I think titanium deuteride is important, because for the longest time ever, I didn't believe in cold fusion, because that field is pretty badly discredited, and you cannot publish in peer-reviewed journals if your topic deals on cold fusion. So I was trying to stay away from trying to explain my results by either evoking cold fusion or low energy nuclear reactions, but I pretty much have no choice but to invoke that explanation now, and my focus is on titanium deuteride, because titanium deuteride is a solid powdered substance that I had suspended in my oil, and I think that deuterium dissolved in titanium might have been doing the fusion trick. So that actually gave me the idea that I need 3 components in my oil. So I need this DTO droplets, because I think those droplets are essential for creating this very, very strong acoustic waves that you saw, those massive spikes. So I think the DTO droplets expand and collapse as soon as they turn on sound to the reactor, and this the shock waves that these bubbles generate, they interfere constructively and produce these massive spikes on the order of tens of thousands of psi. And then I think that this DTO vapor bubbles, when they collapse, they generate these jets due to instabilities, and these jets impinge on solid titanium deuteride particles, basically impinge on solid surface. And I have fusion inside the solid titanium deuteride particles in solid phase, as opposed to the bulk of the liquid. So that's my working theory now. And one of my goals is to make the bottom plate of my reactor, to which the acoustic piezoelectric driver is affixed, make it out of titanium, and coat the surface with titanium deuteride to maximize the area for the vapor bubbles to impinge upon. Well, that's high on my to-do list. I haven't quite gotten to it because the machine shop haven't made me the part yet, but that's what I want to try. And in the meantime, I started manufacturing my own titanium deuteride powder. So in the past, I relied on a powder made for me by Alan Smith, and he used electroloading of that powder. So by running electric current through titanium chips in electrolyte, he was able to load those chips with deuterium. I don't think it's necessarily the best way of doing it, so I decided to make my own powder, which I made using thermal loading. Basically, I took this aluminum cylinder and I deposited titanium sponge in it, which is just a powder, very fine bubbly powder, and then the heater at the bottom was heating this titanium deuteride sponge to about 400 degrees centigrade. And so these are the wires from the heater that went into the transformer, and into that cylinder I introduced deuterium through from the lecture bottle, basically. And as titanium powder reaches the temperature, and the deuterium gas is absorbed, and what you get is this black titanium deuteride powder. So I started making it, and I started experimenting with it. And one of the experiments was if do I have any neutrons when deuterium is absorbed by the powder? And that's what this picture is about. So you see this massive neutron detector with 10 12-inch neutron tubes running my software, and blue here is the background and red is the experiment, meaning that's when I apply heat, and titanium powder starts absorbing deuterium, and I wanted to see does that cause nuclear fusion inside the solid deuterium? And unfortunately, the answer is no, because you can see that the blue bars are about the same height as the red bars, and there is no statistical difference. But it was fun to me to try, and now that I have that powder, I can actually try it in my experiments. But there could be some other reasons why this why these neutrons occur. And this reminded me of the work that my colleague in Russia has done. And what you're looking here is his reactor, which is also oil-based. Unfortunately, he didn't use deuterated oil. He didn't use deuterium or water droplets. But what you see here is a nozzle. And what you don't see is the high-pressure pump. So he was feeding his oil through the nozzle at very high pressure. So the oil was exiting the nozzle at very high velocity. And you see it actually glowed. He doesn't know why it glowed, but I think it glowed because oil is dielectric, and when dielectric rubs, in this case it rubs, the oil stream rubs against the bulk of the oil, and you have charge separation. So I think this glow is electrostatic in nature. And I'm very keen on trying this experiment, except I'm not keen on trying it at home, because if the oil spills, it will ruin my home laboratory. But I am really interested in this experiment because it's a similar effect to what I've seen in my reactor. I've seen oil receiving massive electrostatic charge. It didn't quite glow in my case, but it glowed quite brightly in his. I'm really interested in combining this idea with deuterium bubbles of deuterated oil to see if maybe this massive electrostatic friction would result in increased neutron emission and fusion. And in concluding of my presentation, and a little plug, now that I published the paper, a lot of people approached me and expressed interest in the project, and that compelled me to create a refunder page for crowdfunding for the microscopic thermonuclear fusion. So here is the URL. If you're interested, you can go to this link, and you can read about all of the details of the public solicitation that's under Reg CF regulation crowdfunding. And finally, to conclude, if you want to read the nitty-gritty details about how this experiment was done, I suggest you start by reading the paper that I published in Nature Scientific Reports on the observation of neutron emission during acoustic cavitation. And if you want additional details on the hardware, these are the next link. So the automated nuclear lab is how the hardware is built. Pulse counter is how the software is written, what is the algorithm for pulse processing and pulse counting, spectrum reconstruction. And finally, the technique for reliable neutron detection that I advocate for my colleagues to use, and it will be another paper ready for publication in the near future. But these are all nitty-gritty details that would satisfy the most inquisitive scientific mind to get to the to the minutiae of how this experiment was performed. So if you have any questions, I'll be happy to answer it.
Well, Max, thank you so much. I'm incredibly impressed. So the takeaway that I have from this is you are testing, measuring, and analyzing a home-built bubble fusion reactor, and you are seeing results. That's giant, right?
Yes. Yes. Unfortunately, I cannot claim like a massive breakthrough in the sense that, I still have maybe, another year or so to go before I know why, this works. Because, reporting results is one thing, knowing why you've gotten them is another. And I'm at a stage where I have reported the results, but I don't quite know, why they are. And that's, the part of the research I'm at. So, maybe I'm trying to be modest, but, that's how I feel. I feel that science is about teaching someone else. And when you teach somebody else, it means you've learned something yourself. So I don't feel like I've learned enough myself to teach or easily to teach, somebody else. So I've shared, what I've learned, but I feel like my knowledge is still partial, and that's what I'm still working on. But that's, how science is. You rarely are able to get to the bottom of what you uncovered like quickly. Usually it takes a while. So patient, and that's what makes science fun.
Oh, absolutely. Well, and it feels like you started with a relatively traditional approach to bubble fusion, right? And
That's
really
correct.
what you're moving into is a completely new area where you're looking at, various mixtures, various changes in chemistry, things that really haven't been investigated before, right?
Exactly correct. Yes, and frankly, um, the biggest criticism that bubble fusion received from researchers when it was published is nobody believed it would be possible because of instabilities, and instabilities plague fusion projects on left and right. It's just hard to create plasma. It's hard to confine it. So when the initial bubble fusion idea was born, everybody kind of smiled and said, well, you'll never get it to work because of instabilities. And that's exactly what I see when I just do bubbles, pure bubbles and pure bubble fusion idea. I never get neutrons. So I started getting neutrons only when I said, the heck with it, let me try, various things, kind of Edison mode. Let's try a straw for a filament. Will it work? And that's really when I've gotten the results. And now I don't think that my results are traditional bubble fusion because of that behavior. How a neutron flux returns to baseline slowly. So there is something else is going on. And so you are correct. Yes, it started with bubble fusion, but the process kind of led me astray from it in its pure form. But I still believe bubbles are important, but for other reasons.
Mm. Well, one of the things that impresses me so much is that you're doing this work yourself, and the audience may not immediately know that fusion research has a rich history of home-built labs, right? I think when we think of nuclear research, a lot of the times we're thinking of the movie Oppenheimer, where guys are secreted away in some government lab with, the windows shut and the doors locked and all that. And maybe back in the day during the war that was the case, but Philo Farnsworth, the inventor of the modern television, was one of the big pioneers of inertial electrostatic confinement fusion, and the fusers that he built are replicated by hobbyists very frequently, right? So this is something where people are doing investigations on their own, and I think a big part of that is having the freedom to pursue other paths.
Yes, this is an excellent point. So let me elaborate a little bit more on it. So, before I started my company, actually for almost 8 years or 9 years, I was a professor at Penn State. So I had an opportunity to engage in academic research, but I never liked it because on one hand, there is this notion of academic freedom, but, once you're in academia, there is no academic freedom because you can only work on research, that is funded. And when I was at Penn State, I was trying to do projects, with my colleagues. So with other professors, we would collaborate and write a proposal. And of course, I was always interested in things that haven't been tried before. That's what is more interesting to me. And we could never get, those proposals funded. And we wrote, tens of them. And it wasn't just me; it was me and my esteemed colleagues, with me, who've gotten funding in the past. Had hundreds of papers. So despite, them, being on board, when you propose an idea that's not an increment on what's being done, it doesn't receive funding. And the explanation I've got is that the reviewers, when they read it, they don't get it because, they read it, they don't understand it, they don't get it.
Yeah.
And they're not comfortable giving money to it because if it was an increment on what they've done, an increment on what you've done in the past, it makes kind of sense to them. Oh, let's give them money. So contrary to popular belief, I'd say universities are places where the least innovation takes place. And not because professors don't want to innovate. It's just they don't get funding for that. And then that was the motivation for me to quit Penn State and start doing the work that I do by myself because nothing limits me here. It's how much money I personally have to spend in it. But the other thing I find interesting is I think the reason mainstream fusion projects are so expensive is because they're so complex.
Yeah.
So these instabilities are very difficult to control, and it takes hundreds of people to figure it out. And that's what I call we're too smart for their own good. So when you have PhDs and postdocs that are too smart, you can give them complex problems and they will keep solving it. But then you have this behemoth of a system that requires 100 people to comprehend it and 200 to build, and everybody needs a six-figure salary, and the equipment costs $1 million, and before you know it's $1 billion. Clearly, this is not the way to do it. So I think enthusiasts, such as myself or other people, we're trying simpler things, something that you can do, on a bench top, with some pocket change, something doesn't require 100 people. And I think it was time somebody, not necessarily me, but somebody will get lucky just because they tried something that somebody else didn't try. And maybe it's not as complicated at the end. I don't think you need to force or rape nature to do things it doesn't want to do. And that's kind of the conclusion from my bubble fusion work. So bubble does not want to collapse uniformly. So when you're trying to make it collapse uniformly, you're forcing nature to do something unnatural. So how about, we let bubble collapse however it wants to collapse, and it wants to produce this jet. So maybe if we leverage that, what it does naturally, and let this jet, let's say, impinge on a solid surface, then maybe all of a sudden it will work. Because we're not trying to force nature to do something it doesn't want to, and instead, kind of go with the flow of all things.
Well, Max, have you considered putting together a replication team? So you talked about funding and you had talked about like working outside of the academic environment, right? And there are a lot of projects basically that start out again in a lab, in a garage, in someone's house, something like that. Typically, you've already started publishing with this. Typically, once you reach that point, then you add other people in to replicate that. And then after you have a sizable number of replications and a better handle on, the minutiae of what's happening there, you can pursue funding. Have you looked at putting together a replication team?
Excellent idea. In fact, one gentleman approached me about replication a couple of weeks ago, and we had a discussion like you and I talking over video, and I walked him through the challenges. And he said he wasn't, what's the word? Said I did not dissuade him from doing the replication, but I haven't heard from him since. So maybe I did. So I need to follow up and see, if he still wanted to pursue it. But, I'm going to be honest about it. It's going to be difficult. So most people want to do, something quick. Like building fuser is quick because, it's been done many times. The recipe is well defined. So this replication is not going to be, as easy. And maybe, that's why not a lot of people have so far expressed interest, except for that one person. But I would like, to see obviously, more inquiries as far as replication goes, because yeah, it would be great to have, a collaborator or two, because, two sets of eyes or three sets of eyes. And this is another point I was going to make. Part of the reason it takes me, as long as it does, is because when one person is working on it, you tend to see the same thing or make the same
Yeah.
mistake. Whereas if you have another person, they see it differently and they make different mistakes. and with enough people, you have like better coverage of, of your senses, of, how you comprehend all the data that's coming in, right? And you try, things slightly differently. So I think, if two or three people were working, it will go faster in like geometric progression. And that's really my dream. That's what I really would like. And that was the motivation to put the project on WeFunder, so I could actually afford, to hire somebody, to work with me full time, because I have no shortage, of experimental ideas. It's just, a lot of work, because on one hand, I need to keep my company going and manufacture, the scientific equipment that I do. And on the other hand, when I have time, I work on this, and you have to decide what you're going to do. You're going to make money, or you're going to spend money that you made on the experiment, right? So.
Well, and it seems like, you'd mentioned a couple of different possible reasons for the results that you're getting. One of them might be fusion, one of them might be something else. But regardless of the reason, you are seeing counts of these particles that are
Yes,
far over baseline, right?
that's
So
correct.
you're
Yes,
getting a unique result. You're
yes,
getting
yes.
something that is worth pursuing.
Yes. So however you look at it, even if it's not going to be a fusion reactor, like in the worst case scenario, you're going to get a neutron source out of it. And a strong neutron source, has a bunch of useful applications, from imaging to nuclear pharmacology. Believe it or not, it actually blew my mind that the town I live in has a nuclear pharmacy. So when you go and do the MRI or CAT scan, they give you contrast agents, and those are, all synthesized at a nuclear pharmacy. So, believe it or not, there is, immediate need for things like this, for healthcare. So even if I fail at building an engine, maybe it will reduce the cost of pharmaceuticals for imaging. Yeah.
Yeah, I think that there could be untold possible applications for it. And again, the fact that you're using new mixtures in terms of working fluid really opens the door to all sorts of new possibilities. Now, I do want to ask about the borax boxes behind you, because I noticed at least a couple of them there. So what's going on with the borax?
Well, the reason I was using borax boxes is twofold. Main reason was I wanted to screen the background neutrons from my detectors, because when you're just starting, you don't expect a lot of neutrons, and then you want to see maybe one neutron over background. So your probability is higher if you reduce background. So boron in borax is an excellent absorber of neutrons. So that was easy for me to go to Walmart and buy all the borax they had to line the reactor. But then, when I started getting, lots of neutrons, it's a good idea to screen them, because you don't want to, irradiate yourself. So that's why it solves two problems. It lowers the background and keeps me safe from whatever neutrons, I may be getting. Because in the past, I've done a lot of work with X-rays, and I wasn't screening myself too well. And, I've gotten some, issues from that. So now I don't want to repeat the same mistake.
Okay, so it's shielding. You're using the borax as shielding.
It's exactly neutron shielding, yes.
Yeah. Again, I just think it's amazing. I love the fact that you were doing this yourself. You're taking action and you were pushing forward with this. So your website is online. I believe it's maximus.energy, and I will drop links in there. You are looking for replication partners.
Yes.
You have already published. I will drop a link into your papers as well. So let me thank you so much for your time today. It has truly been a pleasure and an honor to speak with you.
Well, thank you for having me, and it's been a pleasure and honor for me as well. Thank you, Tim.
Wonderful. Thank you again, sir.
Bye-bye.